From glass habitats on the moon to starshades that could reveal new Earths. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. This week, we're taking you inside NASA's Innovative Advanced Concept Symposium, where visionary thinkers share ideas that sound like science fiction, but could become the next great space missions. This was my third year hosting the webcast at the symposium, this time in Philadelphia, Pennsylvania, from September 9th through the 11th. I had the chance to speak with some of the scientists and engineers that are daring to push the limits of what's possible. This is going to be the first of two episodes highlighting projects from the 2025 NIAC Symposium. In this episode, we're going to explore bold ideas on space structures and observation. The next week, we're going to turn to robotic exploration and some brilliant ways of studying worlds like Venus. First, we'll meet Martin Bermudez, CEO of Skyeports LLC and principal investigator of the LUNGS project, alongside Josh Simpson, who's a glass artist and co-investigator. Together, they're exploring how we could one day build lunar habitats by melting and blowing moon dust into massive glass structures. Then Christine Gregg, who's a research engineer at NASA Ames Research Center, is going to share how architected metamaterials could stabilize enormous lightweight space structures. It's technology that could help us one day build giant telescopes and starshades that are more efficient and dynamically stable. And finally, John Mather, Nobel laureate and senior astrophysicist at NASA's Goddard Space Flight Center. He shares his vision for an inflatable starshade that could help us directly image Earth-like exoplanets around distant stars. Then stick around for Bruce Betts and What's Up and a new random space fact. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. NASA's Innovative Advanced Concepts program, better known as NIAC, exists to give bold ideas a chance. Each year, NASA funds visionary concepts that could one day revolutionize the way we explore space. Every project begins as a phase 1 study, where researchers test whether their ideas are even possible. Those that show real promise move on to phase 2. That's where the designs get even more detailed. But only the most transformative concepts ever make it to phase 3. Paving the way for real missions that can push the frontiers of what's possible. The proposals range from plausible to astonishing. Propulsion systems for interstellar travel, self-assembling spacecraft, even habitats made of living materials. Some of NASA's most exciting technologies begin right here in the NIAC program. One of this year's Phase 1 projects takes the spirit of imagination to the moon. It's called LUNGS, short for Lunar Glass Structure Habitats in Low Gravity. The idea is to build lunar homes, not from metal or regolith bricks, but from glass melted and blown directly out of moon dust.
Thanks everyone for being with us this afternoon. I'm here with two people from the LUNGS project, that's the Lunar Glass Structures Project, Martin Bermudez and Josh Simpson from Skyeports. They're the PI and co-PI on this project. First off, I want to ask you, because I'm one of those people that loves watching glass-blowing videos online. I find it such a beautiful art form. What inspired you to use this as a potential for building habitats on the moon?
Oh my God.
Well, from a glass point of view, we realized that lunar regolith, the soil that's already on the moon in situ, is 50 to 62% silica. And with silica, you can make glass, but lunar regolith also has glass stabilizers like calcium and magnesium in it. So by adding just a little bit of flux to that lunar regolith, we were able to make glass that you can actually blow. And it's liquid and it's at 2,100 degrees Fahrenheit. My part of the job was to try to formulate a glass that would melt and could be formed into something useful.
Yeah, you know what? First thing we thought, you know what? This could be the next home up on the moon. You know, if you could, blow this kind of glass up on the moon using from the in situ resources, right? I mean, because like what George said, mostly silicates and minerals and metals. So if you can do this kind of size in 300 meters, 500 meters, and I don't know, possibly a mile, and we can blow it up there. Because you know what, the conditions are pretty good. Low gravity environment, and you got in situ, minerals and everything. So it could be feasible. Is that beautiful?
The whole idea is that when we go back to the moon, which we will do, right now we'd have to bring everything with us, not just our food and our clothing, but we'd have to bring structures to live in, habitats. But if we could use materials that are already on the moon, in situ, that would be weight that we don't have to take out of Earth's gravity well to make structures. And so on the lunar surface, a lunar day is 14 Earth days long. There's sunlight, there's no atmosphere, there's no clouds to interrupt solar cells or solar panels. We could make electricity, we could build a furnace, and in 1/6 gravity, in a vacuum, it would be easier to blow a sphere, we think.
Yeah, it reminds me too of like all the futuristic drawings I've seen of habitats on the moon are like these beautiful glass domes, and that's something I've always wanted for the future. But most of the ideas that use in situ resources are some kind of 3D printing out of lunar regolith, something where it'd be very difficult to have this kind of like glass and be able to see through to the sky.
Right. You know what? That was at the beginning when the idea, it was like, okay, is it going to be a challenge or how is it going to be? So we started thinking and doing the back of the envelope measurements. And so I said, low gravity, 1/6. All the conditions are pretty good to blow it out. The idea is to actually build a furnace here on Earth and have it, designed to blow it. To have a system like this, not only with one shell, but it could be multiple shells inside this one.
Having multiple shells would be one way to protect against gamma radiation or other radiation, sunlight even, and having multiple shells and perhaps putting lunar regolith in between the shells would help insulate and protect the habitat.
Yeah, because that brings me to my next question. Like I was thinking about this, the idea of putting glass in space sounds beautiful, but we're dealing with the radiation environment. We're also doing exactly micrometeorites. As much as that's wonderful, it's actually part of what helps us produce these glass beads on the surface of the moon. But that being said, like I was worried that you would need a really, really thick shell or maybe multiple shells. So it's really wonderful to hear that.
Yeah, and there's no reason why the shell would not be thick. It would be harder to break it. Also, we're talking about using one of the fluxes would be a boron flux, which has a low thermal expansion. So it wouldn't expand or contract very much in the different temperature environments on the moon, from plus 250 degrees Fahrenheit to minus 240 degrees Fahrenheit.
Absolutely. If we want to tackle all the environment, harsh environment of temperature swings, thermal shocks, moonquakes, I mean, you name it. And somehow we started doing some research about the thermal possibilities of this glass, micrometeorite impacts, because the ISS uses some type of glass like this, not exactly like this. So we thought, okay, you know what? Maybe we can make a super glass material there on the moon, in situ, SRU. So yeah.
You could incorporate different kinds of, metals and materials from the lunar surface as well into the glass. Is that something you're exploring as you're testing kind of the structural integrity of these bubbles?
It's something that we've thought about. We have not explored it yet. It's just, this is the very simple start of this. We're phase one, and we're looking forward to pursuing it further in the future, we hope. And it's certainly fascinating to think of. I am not a glass scientist. I'm an artist, and I've been a glassblower for more than 50 years. But this has been an experience for me to use raw materials, where usually I'm trying to make materials that have gorgeous color or optical properties. But in this case, I started with a material that is just foreign. And actually, it was wonderful. There are companies that replicate lunar regolith very precisely chemically, high fidelity simulants, and so we were lucky to be able to use that. I wanted to ask NASA for the original samples the Apollo people had brought back from the moon, but they were reticent about that, giving us that.
Yeah, just as a follow-up, Josh, There is a lot of metals. You got titanium, you got your aluminum, you have magnesium. So yeah, we can create a pretty good strong glass. If you do the mixture, and there's some of the other minerals that we know they're there. Also metals like graphene, it's also there. Zirconium is almost there. So phase 2, we're hoping to integrate some of those and do some more study about the chemistry. Yeah.
There are also problem metals, like we have iron, a lot of iron, and that's the reason this is a greenish color. The reason Coke bottles on Earth are green is because there's iron contamination in the sand. And so that's something that we have to contend with. And there are ways to decolor the glass, but iron is one of the things that we have to deal with.
Perhaps I can show that one too.
Yeah, this is a much darker glass, and because there's even more iron in the lunar mare glass. Lunar glasses consist of silica and anorthosites, ilmenite, a bunch of different stuff things that don't want to melt naturally, or they take a very high temperature to melt. But so this is the lowland glass, the mare glass, is going to be darker until we figure out more about it.
Yeah, it's more basaltic, this one. More volcanic rocks than just this one. So you can see the difference. So if you put it together, yeah, you can see the difference.
It's a little thicker also. This is melt number 19. This is melt number 21. So we had to experiment with adding different fluxes and melting over and over again at different temperatures to see what would work.
This is smaller scale. When we're talking about putting humans in this situation, we're going to need much larger glass objects.
Well, we need smaller people.
Smaller people. Just downsize everyone. Wouldn't that solve a bunch of our problems? But in order to melt that amount of glass, you're trying to come up with some kind of microwave system for melting the glass. What kind of robotic or human presence would you need on the moon in order to operate that, to melt the glass to begin with?
That's an interesting question. When we started,
we don't know.
Yeah, a lot of things we don't know. Josh is absolutely right. When we approached NIAC and we said, we could mine it ourselves, and they said no. Let's think about building the habitat and make sure that the glass blows and it follows the rules, physics rules, chemistry, the mineralogy, so everything like that. So the human presence should be robotic at the beginning. I think we just working on the furnace first, but then there have to be some mining company doing the mixture for us, because the impurities could play a real role there too. So we need someone who's just actually specialized in giving us the right amount that we need, because Josh has been working on this mineralogy for a little bit, so he knows all the what we need: a little more titanium, a little more aluminum, magnesium. So yeah,
I think it would be robotic, but controlling the grain size. For example, if you're mining lunar regolith on the moon, if you pick up a rock that's this big, it still needs to be crushed or dealt with some way to make a grain size that can melt. And that's a challenge that we have to deal with. But we are thinking that on the moon, you could make a great deal of power with solar panels. And we could melt literally thousands of pounds, tons of glass. On Earth, we make very large sheets of glass, 15, 20 feet across and 500 feet long, and we use it in buildings all the time. There's no reason why we can't engineer something that would work in 1/6 gravity in a vacuum. Actually, the vacuum would keep a lot of the impurities on Earth are bubbles that form from carbon dioxide or other gases that form inside the glass. That would not be a problem on the moon.
Although it occurs to me that, while I'm thinking it'll be easier to blow a sphere of glass in low gravity, testing something at those scales on Earth is going to be a real challenge. Do you have some idea of how you're going to begin to test this kind of thing?
I have started some drawings of how you would create a furnace, or in this case, I'd probably ladle a large amount of glass into something that would hold it with a tube that comes up from underneath and would blow a sphere. There are complications in that in Earth gravity, and in Earth pressures here at 14.7 pounds per square inch. In a vacuum, that's an easier thing to do. You could blow it with very little pressure. But these are things that we need to work out in phase 2.
Yeah, you guys are just starting. You've got time to figure it out.
Plenty of time to blow some more glass. Next I think we should, like Josh said, to start working on the prototype and see if we can utilize maybe the ISS or the parabolic, plane, so just to prove, in microgravity, or in vacuum conditions. But eventually, I think it will be really cool if we can bring it to the moon, the prototype, and just test it there, just to see if how it blows and how big. So
Yeah, but when I'm envisioning future habitats on the moon, they're usually like half a dome, not an entire sphere.
So the idea is, if you notice the piece below, right? So that would be the furnace. Let's say the furnace is about 8 meters wide by 15 meters tall. So what we're going to do, and the idea is to utilize the actual furnace and take out all of the essentials for the blowing and everything else, and use it for the egress and ingress to interior to go in and out. So think about, this should be like the top of the furnace, so it's empty. So we could have the main core or elevator connected from the bottom of the furnace. So we're basically using the furnace itself as a platform, so together.
And there would be enough room through the center of the furnace to actually have an elevator for people from the surface of the moon to go up to whatever level they were going to.
See, that totally answers my question. I'm like, how are you going to do that? No, that's really clever.
This may sound crazy now, but 50 years ago, the idea of a cell phone or a watch that you could talk to was also crazy.
No, I think that is the beauty of the NIAC program specifically, is the fact that it's willing to give this kind of funding to things that might seem super future thinking, might seem crazy, but imagine the benefits for humanity if it was just as simple as blowing a glass dome on the moon, right? That would completely change our ability to build permanent settlements.
Absolutely. We don't know how big this can get. We don't know. There's so many unanswered questions, and we would love to go into second phase just to try it. But we're confident, But this is the first step. We were able to blow it, and that's one great thing. So that's one big step. Yeah.
Actually, we are taking just baby steps, but what we have absolutely proven is that you can take lunar regolith and make a glass that can be formed. And if we couldn't do that, then we can't go anywhere. So at least we've taken this small baby step.
Yeah, absolutely.
Yeah, and if, we're thinking about this on the moon, but perhaps someday, once this is proven out, there are all kinds of worlds all over our solar system that have those kinds of silicates in them. You could build these kinds of habitats everywhere, but it's very useful to be in on a world that's nearby us where we're already hoping to build permanent settlements. Well, thank you so much for this innovative idea. It might just be the fact that I love glass blowing art, but I love this idea. It's absolutely fantastic. Thanks so much, everyone.
The Lungs Project captures what NIAC is all about, turning something as ordinary as sand into something extraordinary, like a home on another world. But the challenges of building in space don't stop at the moon or with human habitation. As we look even farther outward, we're going to need enormous structures, vast telescopes and delicate starshades that could unfold or even assemble themselves in orbit. To make that possible, engineers need materials that are both incredibly light and remarkably stable, able to resist vibrations and hold their shape over time. That's where Dr. Christine Gregg comes in. She's a research engineer at NASA Ames Research Center and the principal investigator of this NIAC study. It's called Dynamically Stable Large Space Structures via Architected Metamaterials. Her work explores how precisely engineered materials could transform the way that we build and stabilize massive observatories and starshades in space.
This is Christine Gregg. She's from NASA Ames, and you're going to be presenting tomorrow, I believe, about structurally stabilized large space structures via architected metamaterials. There's so much going on there. So before we talk about what metamaterials are and about the complexities of that, I want to talk a little bit about this idea of direct imaging of worlds, which is one of the things that you're hoping to help accomplish with this.
Yeah, so one of the most exciting things that we want to do for sort of astrophysics and science is try to look at exoplanets that are in what are called the habitable zone. So this is an area that's actually relatively very close to stars, where planets could theoretically have liquid water just like our Earth. And we think this is a really great place to look for life. Because the best life that we know how to look for is the one that's based on water, like ours.
Yeah, I've been talking a lot about directly imaging other worlds in Planetary Radio in recent months. One, because we're all looking forward to this idea of the Habitable Worlds Observatory, which, if it happens, is going to be a project that's going to allow us to actually directly image other worlds, maybe even Earth-like worlds. But we did have a big story come out in recent months about the YSCS-1 system, which was the first multi-planet system around a sun-like star that was directly imaged using the European Southern Observatory. So I've been getting a lot of questions about this, but I'll put this to you. Why is it so hard for us to take images of these worlds going around other stars, particularly the smaller ones?
You know, there's a paper that I referenced, and you'll see in the presentation tomorrow, that, you know, if you wanted to look for Earth at around a star that's like our sun, that's about 30 light years away, it would be 10 billion times fainter than the star itself and be very, very close to the star. So that's basically like trying to image a firefly, the light from a firefly, at high noon, directly next to the sun, when the apparent distance is the width of a human hair at 200 meters. Like, it is just a very difficult task to do, and you have to find some way to block all of that starlight and try to get the very faint light that's being reflected from that planet. And so, you know, we've got a lot of different ways that we can do imaging. And one of the very exciting things that's coming up with the Nancy Roman telescope is going to get first glimpses of reflected light from planets that are about as big as Jupiter. So there's a lot going on in the space, and we're all very excited about habitable worlds. The mission that we're looking at is trying to figure out, okay, how can we look at those Earth-like, those Earth-sized, very close, very small, relatively planets?
Well, we're currently able to directly image other worlds using coronagraphs, which essentially block out the starlight like inside of the instrument itself. But you're proposing using these kinds of metamaterials to make star shades. What is the benefit of using a star shade rather than using a coronagraph?
One of them is that they're much larger bandwidth. One of the things that we're excited about with the particular mission is that we should be able to get really high sensitivity, especially working with this hybrid observatory concept that we're looking at, using very large Earth-based telescopes so that we can get a lot higher sensitivity relative to current coronagraph proposals that I've seen.
But see, the challenging thing here, right, is that in order to build a star shade, they have to be pretty big, and that's where these architected metamaterials come in. So can you tell us a little bit about what are these metamaterials, and specifically, what are phononic crystals?
Okay, so I'll just answer generally. So metamaterials in general refer to this really large body of work where people have figured out ways to engineer the substructure of different materials to be able to get really exotic properties that we don't see on Earth normally, or materials that you just sort of mine out of the ground. And so there's lots of different types of metamaterials, phononic crystals, basically changing the way that waves, or whether that be acoustic waves, light, travel through these materials in really odd ways, versus just mechanical metamaterials, which is accessing stiffnesses and strengths that we otherwise couldn't in natural materials. So it's a huge field. What we're focused on is actually an area of metamaterials where we're trying to control what different vibrations, sort of what different modes are allowed to go through a material, as well as looking at ways, can we get this material to damp out vibrations? And so we typically call those dissipative metamaterials. And so it's figuring out ways that we can make materials that are very stiff, but also able to dissipate and get rid of energy and reject that energy so we can damp out vibrations.
Why is it so important for us to have these kind of structurally stabilized materials that can damp out, why is this a bottleneck for what you're trying to do?
You know, in space we think about we can make really lightweight structures because we don't have gravity, right? That's one of the nice things about space. But the problem is that we don't have otherwise ways to get rid of vibrations that are just going to be coming from disturbances, from your reaction wheels, just in our case, really aggressive sort of station keeping maneuvers. And so this, you have to imagine, you've got this very lightweight floppy structure, it's going to keep vibrating for a really long time. And so you run into this situation where the mass of the structure is limited by how well you can engineer the dynamics of the structure, not necessarily the strength. And in this mission that we're thinking about, again, we're going to be doing quite aggressive station keeping maneuvers, but we need this thing to be quite precisely shaped to do all that diffraction control and do the optics and the science that we want to do. So we're looking for ways that we can use these, again, exotic metamaterial design properties to see if we can get it to settle very, very quickly and allow us to get more science.
Usually we're limited in the size of objects that we can send to space. Say with JWST, we had to origami that thing up into a spaceship just to launch it. So is it possible to make these things kind of retractable or compressible, or do they have to be monolithic to have the correct damping to do what you're trying to do?
Yeah, there's no way it's going to work if it has to be monolithic in 100 meters. Yeah, no. So, a lot of amazing work has been done in the deployable regime for starshades. What we're looking at is seeing if we can use robotic assembly to be able to more easily work in these sort of exotic designs of the metamaterial. So a lot of my prior work was on robotic assembly of different architected lattice and different mechanical metamaterials. And so we're trying to bring that aspect of it so that instead of having a complicated deployable, which are incredible but very anxiety-inducing for me, and sort of lean on the advances in robotics and actually construct it in space. And it gives you a little bit more design freedom because you don't have to have it fold up so nicely in a fairing.
I love this idea of just building things in space. It would take so much of the troubleshooting out, so much of our space construction.
Absolutely. Yeah, I'm too nervous for deployables.
Yeah, anytime we send something up there that has like 200 plus points of failure, I'm just sitting on the edge of my seat, losing my mind.
I'm with you.
But beyond starshades, what are some of the structures that we could use these kinds of materials to, build in space and hopefully extend our ability to learn more about the universe?
So a lot of structures in space are actually dynamics limited. It's a large issue with even solar panels where you have these thermally induced vibrations and you need them to damp out. And so I think if we understand how we can work these design principles using materials that are qualified for space and designing them for robotic assembly, sky's the limit.
Why did you guys decide to start with something like a starshade versus other technologies?
One, starshades are amazing. They're so cool. So, I think we'll all jump at sort of the opportunity to work on something as exciting as that. But it also, again, this is a unique mission concept that was actually a prior NIAC by John Mather, looking at using a really large starshade with an Earth-based observatory. And so, again, starshades have been around for a while. This is a pretty unique mission context for a starshade. Again, most starshades, you can wait a very long time for them to settle out vibrations because you don't need to sort of formation and fly them with an observatory on the ground. And so this was a very unique application where it was a very dynamic environment, very sensitive to mass. And so we thought it was a very challenging but high reward place to see if this technology could help.
Could this actually help us lower the mass on our ideas of how we can build starshades? And how big of an object are you conceiving that we could build with this?
Well, the thing about assembly is that, if you start combining it with things of being able to send multiple launches and doing rendezvous, there's no real theoretical limit to how big of a thing that you can make. And I think that's what makes me really excited about in-space assembly in general. It starts getting to, all the science fiction literature ideas that I think we all found really exciting. And so right now we're looking at a 100-meter structure, which would be one of the largest structures ever flown. So it's quite big. And yeah, the hope is that it reduces the mass. So we'll see. We're early in our project, but that's what NIAC is all about, seeing if these crazy ideas will actually work.
Yeah, today a starshade, tomorrow a full Dyson sphere.
Yes, well, you laugh, but that's, I think, what attracts a lot of us to this field.
How are you going to be testing these materials here on Earth to see if this is a viable way of constructing large-scale structures in space?
Yeah, so I'm working with really amazing collaborators at the University of Michigan, at the University of Texas at Austin. And so they're very experienced at doing tests both in air and also in vacuum, looking at the vibrational characteristics of these structures with and without sort of the metamaterial design approach. So there's a lot of testing that we can do here in analog environments. But ultimately, you're right, we do need to sort of work our way through a very rigorous testing regime, making sure everything works at the temperatures and the pressures that we're going to see out at L2 where we want to go.
So what are the next big steps for the project as you're entering this world of NIAC that you're really looking forward to personally?
Yeah, so I think we spend a lot of time really trying to understand what the requirements are going to be. You know, I think at the end of the day, we're engineers, and any engineer knows that you have to understand your requirements before you can come up with a good design. And so we're just starting to really get into the meat of the design phase and really figuring out what this structure is going to look like. So all the pictures you'll see tomorrow are notional at best, but we're getting into the really exciting part. So that's great. Very much looking forward to it.
We'll be right back with more from the 2025 NIAC Symposium after this short break.
For over 45 years, members of the Planetary Society have teamed up to crowdfund science and technology projects like LightSail, the 100 Earths Project, PlanetVac, and so many more. The STEP grant program continues that concept but uses an open call for proposals to cast our net far and wide to find the best projects. The first 2 rounds of STEP grant winners have done great stuff, ranging all the way from developing a new technique for studying near-Earth asteroids to doing a careful comparison of different ways to grow edible plants in space. We're once again going to invite the brightest minds worldwide to discover the next breakthroughs in our 3rd round of grants, and we need your help. This vital scientific research will be made possible with your support. Right now, funding cuts at NASA and the National Science Foundation are threatening scientific research. There's never been a more urgent time to support independent scientific funding. This is real space science and technology funded by you. Donations given today will go directly to the next round of STEP grant winners. Please join us in this crucial endeavor by making a gift today at planetary.org/step. Thank you.
As Christine explained, there are many ways that we could tackle one of astronomy's most daunting challenges, directly imaging other worlds. Her research builds on earlier NIAC concepts, including one that was led by Nobel laureate Dr. John Mather. His team explored the idea of pairing massive starshades in space with ground-based telescopes through the Hybrid Observatory for Earth-like Exoplanets project. But now he's back with a new proposal. An inflatable starshade that could unfold in space to block starlight and reveal planets that are like our own. It's a lighter and simpler way to pursue the same goal, to see other Earths against the backdrop of stars.
Well, I've said your name is John Mather, but you are a senior astrophysicist at NASA Goddard. You're also Nobel laureate and the senior project scientist emeritus for the James Webb Space Telescope. We're not going to be talking a lot about JWST presently, but I just want to personally thank you. I've been looking forward to this telescope since I was literally 9 years old.
Oh my goodness. Well, so yeah, we started this when some of us were kids. And we started it in 1995. That's when I joined the project. And other people were starting even long before that, envisioning what we would need after the Hubble went up. So we knew a long, long time ago what we had to build to do this. And now we finally did it.
We're going to be talking about this idea for a new type of starshade, specifically an inflatable starshade for Earth-like exoplanets.
Well, a starshade casts a shadow of a distant star onto the telescope to seek the starlight out. So that's important because stars are billions of times brighter than the planets we want to see. So you can't see them unless you keep the starlight out. But if you can, then you can use an ordinary telescope. Doesn't have to be perfect, just has to be pretty good. And you can use telescopes that we're building today. That's the most important part because we are currently building a telescope on the ground in Chile. It's 39 meters across. It's 6 times as big as the Webb. 6 times as big as the hypothetical Habitable Worlds Observatory, and it is so enormous that if we could do this, we could get a picture of another solar system in 1 minute. 1 minute. And in an hour, we could get spectra of those planets to see if they have molecules like oxygen and water, and that would be so cool.
Most people, when they think of a starshade, are talking about deploying some very large-scale structure in space, and there's a lot of issues with that kind of thing. But you're proposing an inflatable version of this. How did you come up with this idea?
Well, we need something that's even bigger than what people used to talk about, because our starshade has to be 170,000 kilometers away from the Earth, and has to work with a telescope that's 39 meters in diameter. So the starshade has to be 100 meters across. That's as big as 2 football fields side by side. So that's hard. And when we get there, we have to push it around with a rocket, because we have to keep it lined up during the observation. Okay, so that's a hard problem. So the lighter the better. So we think, and an inflatable one that you could sort of fold up into a little box and then blow it up to the right shape would be a good answer. So that's hard to do, but we think we can. We have a design we're going to reveal soon, and if you can do it, then you can get the cost down, you can get the weight down, you can use ordinary rockets, you can fly more than one of them, you can see another planet every day.
I'm seeing a pattern in your career here, which is that you're trying to build things that are just so far beyond the scale of what we normally do with these kinds of things.
Well, the first 2 that I did, the COBE satellite and the Webb telescope, those are both in the range of normal engineering. But this one is a little beyond that. We just don't really know how to do this yet. That's why we have NIAC funding to explore what's not impossible advanced concepts. So that's NIAC to me.
What are the things about these Earth-like exoplanets that you're hoping to learn with this technology?
Well, are they the right size? Are they the right temperature? Do they have the right color to be even a little bit like Earth? Are they green and blue? Do they have clouds? Do they have weather? Do they have oxygen and water? Here, oxygen is very reactive. It would all disappear in a few thousand years if there was no photosynthesis. So if you found a planet that had a lot of it, you'd say, well, I can't imagine how it could happen except by life. Now, was Earth always like that? No, we didn't always have photosynthesis here, so we had life long before we had a lot of photosynthesis. So if we don't find it out there, it doesn't mean the planet's not alive, but you can at least have a chance. So if we look at enough planets, then we have a chance to see, well, 10% of them have oxygen. That would be so cool.
It would be. I mean, this is a fundamental question, and I think drives a lot of the public engagement in science. As people who love astrophysics and cosmology and planetary science, I'm going to get excited about a rock. I'm going to get excited about supernova. But I think for most of the people on Earth, when they think about space science, it's 2 things. It's either human exploration or it's this question of the search for life in the universe.
Well, this is human exploration. We travel at the speed of imagination. So we're going to go and see if there's a planet over there that would be like Earth. Does it have continents and oceans? Does it have clouds? Does it have weather? Does it have the right molecules to be at a little bit like Earth? And we're not going to go there in person. You can't. It's just too dang far. But we can find out about them with telescopes.
What are you envisioning material-wise for building this starshade? There's many different things you could use in space. So what are you conceiving of?
Well, we have in mind something called Kapton, which is an aerospace plastic. It's a little bit like Mylar, which you make your Coca-Cola bottles out of. It's really tough, really good for aerospace, and that'd be the thing that we use to make it opaque, to cast a big shadow. Then you need probably something else to make the ribs that you're going to inflate, to make something stiff. So that's not the only thing you need is the big sheet of plastic, but that's most of it.
And what would you inflate it with?
Probably water, or which is nice because after it's cold, it's not there, or lots of gases, whatever is lightweight. You need low mass for our aerospace applications. So nitrogen, pretty ordinary.
How would you actually keep it in place?
We actually need rocket engines on it to move it around from place to place. During the observation, we have to fire the jets because the observatory on the ground is accelerating while we're taking a picture. So in order to keep the thing lined up, we have to put a force on the starshade to keep up with it. So that's number one. And then when we're done with observing planet X, whatever it turns out to be, then we wait for the next orbit to go around. Either we look at it again, or we change the orbit so we can line up with some other star. that might have a planet. And so we need different kinds of propulsion for this. First, probably we're going to use hydrogen through a heater, which gives us the best possible performance, and it doesn't look like molecules like oxygen. That's good, and I just learned about that here at the NIAC meeting. And then in between times, to go to another orbit, some kind of solar electric propulsion, which is now much more mature than it used to be. We can buy the engines that we need already. They've got them on the power and propulsion module that was built for the Lunar Gateway. So we know we can buy the solar cells, we can buy the engines, we can buy everything we need to make it. And the hard part then is just the big mechanical structure, something 100 meters across, which is as big as a couple of football fields, as big as your baseball game. So, this is something that's kind of hard to test on the ground. Maybe you won't test it fully on the ground because it's too big. Maybe you just have to build them and put them in space and see if they work. Inflatable is good because it's not necessarily expensive.
This is a little more simple, although it sounds like the rigid structure underneath is still something that you're going to need to be able to kind of collapse into a rocket.
Yeah, this is not simple. So we're going to be worried until we know that it's going to work. With the Webb telescope, we knew it would work because we did everything we should do. We tested and tested and tested. That's not quite so possible with this one. So we might need to have a series of space tests rather than a series of tests on the ground. It's just something that big and that lightweight. How are you going to test it on the ground? Not in my backyard. So somewhere else. We may have to go into space for the proper tests. Okay, toss it overboard from the space station or something like that.
Well, you mentioned that there are ground-based telescopes that you're hoping to use this with, but there are several space-based telescopes that people are hoping to build that might be able to implement some kind of starshade. What projects are you hoping that might be able to use this technology?
In principle, any telescope in space could use a starshade. But you have to sort of plan ahead a little bit because you got to make it possible to line up exactly. So you need a little help from the telescope. So we need a feedback system, including the telescope itself. It's got to cooperate. Otherwise, it's a lot harder. So in principle, we could have done it with a Webb telescope, but it was too late and we can't make it cooperate. The Nancy Grace Roman Space Telescope is in principle possible, but it's too little to really do very much about this. It's not a big telescope. The Habitable Worlds Telescope, when we put it up, it's about a 6-meter diameter telescope, and it could perfectly well work with a starshade. And it would not need such a bigger one because it's not such a big telescope.
Are there any particular systems that you're really intrigued to hopefully use this technology on? As someone working on the telescope, I'm sure you have all kinds of targets that are in mind.
Well, the best targets are the ones that are around stars like the sun, because the sun is not hostile like the little M dwarf stars. So it also lasts a long time, so it's not going to burn out quickly like bigger stars would do. So we're sort of in the sweet spot as far as we can tell. So look at stars like the sun, which are very common. There are about 2,000 stars that are in the catalog that would be really good to look at. And some fraction of them are the right kind of star, and maybe 20% of them will have an Earth-size, Earth temperature object. So if we're lucky, we know in advance where to look. If we're less lucky, then we'd have to look at all of them. But we'll just start at the middle, start close to home, and look at the nearest ones, and then work out farther, depending on what we see.
As I was learning more about this project, I read basically that coronagraphs have an issue with trying to learn more specifically about the UV light coming off of these worlds. Can you talk a little bit about why that's a limitation and why it would open up new forms of science if we could actually see the UV light coming off of these worlds?
Yeah, sure. Ultraviolet here on the Earth, we don't get very much from the sun because we've got ozone to protect us. And we care a lot about that. Well, if you were looking at a planet from a distance, you'd like to know, does it have ozone? It's a sign of oxygen. So that's a really good marker for something like Earth. And other molecules also absorb a lot of ultraviolet, so you'll be able to tell about molecular chemistry from a distance. Also tell something about clouds. Venus is bright white because of clouds, but there's sulfuric acid and other things in there. So learn about the chemistry of an atmosphere by covering all the wavelengths you can possibly get at. So coronagraphs are hard to build for the shortest wavelengths. It's just harder, just a whole lot harder. So we don't know if they can work, or at least in our lifetimes. We know they can work at longer wavelengths. So we do what we can with what you can build at the moment. In principle, a starshade could be very good at ultraviolet wavelengths, and You can see a little bit of ultraviolet from the ground because otherwise we wouldn't get sunburned. So it's an interesting problem. We're not ready to tell you whether we can do it or not, but we should try. It's a wide open opportunity, and we don't think anybody else can do it.
What do you think are going to be the hardest engineering hurdles to overcome with deploying something like this?
Well, anything that's big and floppy is going to be hard to manage. We might use cables to stabilize it. Well, anybody who's ever been fly fishing knows that's tricky. So you have to be really thoughtful about cables and about unfolding a big plastic thing. So you're going to have to practice.
Well, you are limited in what kind of testing you can do here on Earth, unfortunately, but what are you looking forward to in the rest of your phase 1 explorations of this project?
We are going to complete the design that we have and then sort of set out the plan for what's the next thing to build. Right now we're not building something, but we're about to have a complete design. So then we're going to have the next thing is a workshop at Caltech in October, and we're going to meet with about 30 people and talk about what have we got and what do we need to have.
I just love the idea that we're this close to having actual star shades and potentially being able to take images of Earth-like exoplanets. I think it might just be that I got my start in exoplanet detection back in my day, not that it was that long ago, but this field has been moving so rapidly that back when I started, you could only find these large worlds around stars, and now we're actually drilling down to these smaller Earth-like exoplanets. It feels like we're about to open up a door into a whole new understanding of habitability in the universe.
Well, it's not instant. It'll take us a little while to do this, but we're NASA, we can do this.
Absolutely, and we're right on the edge of 6,000 confirmed exoplanets, so you've got plenty of targets to work with. Well, thank you so much for sharing more about this project with us, and just for a lifetime of excellent work that's taught us so much more about the universe. It really is a strange thing for me after seeing your name on so many papers and articles to finally get to talk to you. And I know you've been on Planetary Radio before with my predecessor, Matt Kaplan, so it's just wonderful to meet you in person.
Well, thank you, Sarah. It's a delight to be here with you.
That wraps up part 1 of our 2-part look at NASA's Innovative Advanced Concept Symposium. Next week, we're going to continue with more NIAC projects that reimagine how we explore the solar system and beyond, from new ways to study Venus to the next generation of robotic explorers and observatories. If you'd like to explore more, you can find links to the live streams for this year's symposium on this episode page at planetary.org/radio. You can also learn more about NIAC and its portfolio of projects by visiting nasa.gov/NIAC. That's NIAC. Now it's time to check in with Dr. Bruce Betts, Chief Scientist of the Planetary Society, for What's Up. Hey, Bruce.
Hey, Sarah.
So I got to speak with so many different people at NIAC. There were a lot of really interesting concepts this year, but one that I've never had anything to compare to was this idea of lunar glass blowing. And I think part of the conversation that we kind of missed, honestly, was how it's even possible to blow glass out of lunar regolith. So I figured I'd ask you, for a little context, can you tell us about naturally occurring lunar glass?
Well, yes, I can. And first of all, which maybe you covered in the interview, this reference to glass, lunar glass, we're just talking about an amorphous, so no crystalline structure mineral or conglomeration of stuff, as opposed to glass. When we usually talk about silica-based glass, that's what we look through our windows, which is an amorphous mineral thing. It can be much broader in a geological context. And so on the moon, you find glass often in little tiny spherical beads, basically, that can be formed by impact melt that then cools and forms these little bead nodules that get spread across the moon, or it can be formed from old-timey volcanic eruptions potentially as well. You even get colored glasses, just to be exciting. That where Apollo 17 went, I think it was orange, but I like to think of it as rose-colored glasses that they would ha 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 ha. And there's some green glass. So we actually have similar things from on Earth, but not all over the place because we have all that erosion and plate tectonics. But we have things glass from impacts. I do want to mention that one thing, that there's a picture that's a scanning electron microscope picture of one of these tiny spherical glass beads, but it's tiny because you have to use scanning electron microscope. And that picture that I often use in classes and otherwise has an impact crater in it. Because there's no atmosphere on the moon, micrometeorites can be super tiny and actually impact other, even slightly bigger things, and create this little tiny impact from a bead that probably came from a big impact. I don't know. It excites me.
No, that's really cool. I don't know. It's interesting. Of the projects presented at NIAC, like this one definitely sticks in my brain, mostly because I've never seen anyone try to do anything like this. But also, I love that people are trying to come up with these ideas for how we can someday live on the moon. And who knows, maybe this isn't the way we do it. Maybe we use a different way, like the mycotecture from the phase 3 project that Lynn Rothschild presented. But I don't know, this is so forward thinking. But one of these days I can just see in my brain scientists scraping through the history of all the ways that people thought to build habitats on other worlds and having a really good time of it.
Hey, I got something new that's old.
Yes.
This show's been running almost 23 years now.
Yeah.
Coming up on the anniversary in just a few weeks. And I've been spitting out, I've tried to have unique random space facts all that time. And sometimes I admit they're getting kind of obscure now and less inspiring. So here I'm introducing the following. Random Space Fact Rewind. Facts so good, we're revisiting them.
All right, what you got?
One of my favorite random space facts is you can fit about 1,000 Earths inside Jupiter, and you can fit about 1,000 Jupiters inside the sun. So you can fit about 1 million Earths inside the sun, very approximately. Those things are huge. Jupiter is huge. The sun is just unimaginably humongous, and it's not the biggest star out there by any means. So it's a wild and weird universe we live in.
Man, that just makes me feel so tiny, but also thinking about the fact that the sun is so small compared to other stars, it's just, I don't know, it's beautiful, but also existentially terrifying.
Yeah, that's really what I was after. All right, everybody, go out there, look up the night sky, and think about an existential happiness. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with part 2 of our look at NASA's Innovative Advanced Concept Symposium. If you love the show, you can grab a Planetary Radio t-shirt at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but it helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, or poetry at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members, visionaries who believe that bold ideas today lead to the great discoveries of tomorrow. You can join us and help shape the future of space exploration at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.